Hello again everyone. Thank you for tuning into part 2 of the video. We looked at the single-phase PV inverter demo model description in part 1 of the video. The link to the first part of the video is given in the description below. Now, let's look at the real-time performance and the multitasking feature in detail. The PLECS coder and the TI C2000 target support package allow the user to generate multitasking code for the TI C2000 family of MCUs. Multitasking code unlocks processing power for controls regulating multiple system outputs with dynamics on a range of timescales. The control scheme here is cascaded with a fast inner current control loop, followed by DC voltage control loop and a slower outer MPP loop. The bandwidth of each loop is separated by an order of magnitude, so the output of the slower outer regulators will change slowly in comparison to an inner regulator. Therefore, multitasking is well suited for this type of control scheme. Multitasking code generation is configured in the Scheduling tab of Coder Options dialog by changing the tasking mode to multitasking. In this model, 3 lower priority tasks, namely the MPP control task, the voltage control task, and the LED task, are defined in addition to the base task. To assign these task configurations in the model, a task frame component is dragged around the blocks of interest. The task frame boundary, combined with the task configuration, define the priority of execution of the components within. All the components outside of these task frames, such as the ADC block, the PWM block, and the current controller, are executed at the base sample time. The scope component is always executed at the base sample time as well, irrespective of the task frame boundary. The TI C2000 application framework includes a rate monotonic scheduler to allow precise and efficient execution of the digital control loops. The shorter the task period, the higher the task priority. Therefore, the base task, which has the shortest period, is always executed at the highest priority. Additionally, up to 15 slower, lower priority tasks executed at different rates can be specified. A lowest priority background task also exists to handle non-time critical tasks. With every control task trigger interrupt issued by the ADC, the lower priority tasks are interrupted and the base task is executed. This ensures that the base task has the highest priority. The additional tasks are prioritized based on the sample time. Once the base task is executed, the voltage control task with the second shortest time period is executed, followed by the MPP control task, and then the LED task. I should mention that the figure is simplified for visual clarity and does not represent the real circuit. In reality, the voltage task is 10 times the sample time of the base task, but not so in the figure. Note that any higher priority task can interrupt a lower priority task. In this case, the base task can interrupt the voltage control task, which can then interrupt the MPP control task. Once these tasks are executed, the system continues with the background task, where lowest priority operations are processed. These background tasks are internal and cannot be accessed by the user through the PLECS coder. If the base task is still executing when a second base task interrupt is received, then the processor will halt and an assertion will be generated. Similar behavior occurs if a lower priority task does not complete by the time it is scheduled to execute again. Assertions can be monitored using CCS debug tools. Assertions can also be detected visually by periodically toggling an LED. If the model is loaded and the LED isn't blinking, it could mean that the processor is halted. This model supports code generation for 4 different launchpad targets. I here have a 28069 launchpad, so I chose this as my target. Note that the target I/O blocks of both the RT box and the C2000 target are functional in the simulation as well and include behavioral model of the component, so that we can verify if the model and the peripherals are configured appropriately before testing on the hardware. First, let's run the simulation offline in PLECS and save the traces. Now, let's run the simulation in real time. As I mentioned in part 1 of the video, this demo model uses the PLECS RT Box to perform hardware-in-the-loop testing of the generated embedded code. Here is the hardware setup. The single-phase PV inverter or plant model is emulated on the PLECS RT Box. And the controller model is built on this red Texas Instruments board, which is a 28069 launchpad. The front of the box contains the interface connections for analog and digital signals. The green board, called an interface or a breakout board, routes these signals from the controller hardware to the box. First step is to build the plant subsystem on the RT box. The discretization step size of the plant subsystem is set to 2.5 microseconds. Once the subsystem is successfully uploaded, the blue LED on the RT box labeled Running should turn on, and the LED corresponding to Digital Out 31 on the green Launchpad interface board should blink. Next, let's build the controller subsystem on the 28069 Launchpad. The execution rate of the base task, in this case, is 25 kHz, or 2 times the switching frequency of 12.5 kHz. If programmed correctly, the red LED on the red Launchpad board should blink. If the LED isn't blinking, make sure the dip switch position and jumper configuration on the Launchpad device are correctly configured. Now, let's enable external mode, which means PLECS schematic is synchronized with an external source, in this case the Launchpad device, as well as the RT box, and see the waveforms in real time on the PLECS scope. I'll flip the dip switch on the Launchpad interface board to enable the MCU. Let's compare the offline and real-time results of the grid during a step change in insolation at 2 seconds from 1 kWh per meter square to 0.7 kWh per meter square. We can observe that the offline and real-time results are in close agreement. This concludes the tutorial video on single-phase PV inverter demo model. For more videos and further information, please visit our website at www.plexim.com. Thank you for watching.